Hello, my name is Samantha Schwartz, and here is my example lesson for math. And I will be going over rules of exponents, specifically multiplying and dividing exponents when you have the same base. So starting with multiplying exponents with the same base, here is our general rule. When multiplying exponents together with the same base, we add the exponents together. So here we have a problem of 6 to the third times 6 to the fifth times 6 squared. We can of course see that we have a common base of 6, and so we can apply this rule. But there's a reason this rule works, and I'm going to go through why it happens the way it does so that we have a deeper understanding of our subject matter. So what this expression is actually representing is 6 times 6 times 6, which of course is 6 to the third, times 6 times 6 times 6 times 6 times 6, or 6 to the fifth, and times 6 times 6, which of course is 6 squared. So at this point, because we want to keep our answer in exponential form and not multiply all the way through, we can drop the parentheses, leaving us with 6 times 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 6, which is a bit of a mouthful, but when we count up all our sixes, we end up with 6 to the 10th. So we can go back and think about our rule of when multiplying exponents with the same base, we want to add the exponents together, and we can see that 3 plus 5 is 8, plus another 2 is 10, so we have gotten to the same place as 6 to the 10th. Either way we go about this. So this is what's actually happening. The rule just allows us to do this more efficiently. So here are some examples for multiplying exponents with the same base. So we have 3 to the fourth times 3 to the sixth. And of course you can see that we have our same base of 3. So our exponents are 4 and 6, meaning we can add them together now and get 3 to the 10th. Another example here, we have a common base of 2, and we have 2 to the fifth times 2 to the 15th. We can now add our exponents together, our 5 and our 15, and we will get 2 to the 20th. And finally, we have 5 to the 21st times 5 to the 23rd. I chose larger numbers here for the exponents to show that no matter how intimidating the numbers may look, as soon as you have the same base, these rules are applicable and you can go through the same simple steps no matter how large the numbers might be. So because we have a common base of 5, we can add 21 and 23 together and we will get a final answer of 5 to the 44th because our base does not change, only our exponents are added together. So now we can talk about dividing exponents with the same base. So the rule for this is when you are dividing exponents with the same base, you subtract the exponent in the denominator from the exponent in the numerator. So here we have 5 to the third over 5 squared. So once again, I'm going to go through what is actually happening here so that we have a deeper understanding of why the rule works. So this expression can also be written as 5 times 5 times 5 over 5 times 5. And now we can see that some of our sets of 5s are going to divide out. You may have previously heard this as canceling out, but I like to avoid the term canceling in math as much as possible because I think it's important to remember that nothing in math ever actually goes away. It simply changes form. So essentially what we have here is two sets of 5 over 5, and 5 over 5 is 1, because anything over itself equals 1. So what we really have is 1 times that remaining 5, which gives us an answer of 5 to the first, but of course we would drop that 1 in our exponent and simply write this as 5. So here we have some examples for dividing exponents with the same base. We have 4 to the 7th over 4 to the 4th. Our base is 4, so now we can look at our exponents. Our exponent in the denominator is 4, and our exponent in the numerator is 7. Now we can subtract that 4 from that 7, and we will end up with 4 to the third. Now here we have 6 to the 34th over 6 to the 21st. Once again, I've chosen larger numbers just to show that no matter how intimidating the numbers may look initially, the same rule applies and we can use the simple steps to go through it. So we have an exponent in the denominator of 21 and an exponent in the numerator of 34. We can now subtract that 21 from 34, leaving us with a 13, so our final answer is 6 to the 13th. Our final example for dividing exponents with the same base is 8 to the 9th over 8 to the 4th. So we have our common base of 8, so we know that that will still be applicable in our answer, and now we will subtract the 4 from the 9, leaving us with 8 to the 5th. Lastly, we can put these rules together and try them in some problems here. For these problems, we will have to remember PEMDAS, our order of operations, parentheses, exponents, multiplication, division, addition, and subtraction. So we have 4 to the 6th divided by 4 squared times 4 to the 5th. So technically, exponents would come first in our order of operations for this particular problem. However, we want to leave our answer in exponential form, so we are going to skip the exponent step that would have us multiply these through. So now, with that, we can work from left to right with this particular problem. So we will start with 4 to the 6th divided by 4 squared. This can be rewritten as 4 to the 6th over 4 squared, and we know that when we have exponents with the same base, in this case 4, we could subtract the exponent in the denominator, 2, from the exponent in the numerator, 6. This will leave us with 4 to the 4th, but we still have that 4 to the 5th to deal with on the end of this problem. So now we have 4 to the 4th times 4 to the 5th, and we know that when we are multiplying exponents with the same base, 4, we add their exponents together. In this case, 4 and 5. This will leave us with a final answer of 4 to the 9th. And for our last problem, we have the quantity 3 to the 6th times 3 to the 5th divided by the quantity 3 to the 4th times 3 to the 4th. So because of our order of operations, our PEMDAS, we will do what is inside the parentheses first. We'll start with the parentheses set on the left, where we have 3 to the 6th times 3 to the 5th. These have the same base, and they're being multiplied, so we know that we will now add their exponents together. This will give us 3 to the 11th, and we still have that quantity 3 to the 4th times 3 to the 4th. So now we can work with that parenthesis set on the right, our 3 to the 4th times 3 to the 4th. We have our common base of 3, and we can take our exponents, in this case both of them are 4, and add them together, leaving us with 3 to the 11th divided by 3 to the 8th. This can be rewritten as 3 to the 11th over 3 to the 8th, giving us exponents with common bases that are being divided by each other, and we can clearly see that 8 is in the denominator and 11 is in the numerator, meaning we will subtract 8 from the denominator, 8 in the denominator from the numerator 11, leaving us with 3 to the 3rd as our final answer. That's all I have for this lesson. I hope you learned something and I hope you enjoyed it. Thank you.